Hello everyone, let me introduce myself. I'm Marine Simwen, a former student of ISP School, where I complete an economics program focused on energy markets. Currently, I work in the economics department of the IFP Energy Nouvelle, the Associated Research Center, as a research engineer. With my team, we are working on the criticality of mineral raw materials in the energy transition, such as lithium, nickel, or cobalt. In this short video, I will try to introduce you to the key elements of this concept. But why should we look at mineral resources in a MOOC related to energy transition? Renewable energies are produced from different sources, such as wind or sun, which are technically unlimited. Nevertheless, as Sine mentioned, these energies are based on technologies consuming an important number of mineral resources that are not unlimited on Earth. And this is true for all low-carbon technologies. Wind turbines consume neodymium, dysprosium. Solar panels require silica, cadmium, indium. Fuel cells, titanium. Electric batteries use lithium, cobalt, etc. And the list goes on. May I continue? Even catalytic converters in thermal cars, for example, consume platinum, rhodium, palladium, and so on. The list is impressive. And nowadays, another sector with a very strong growth is also one of the first consumers. It's the digital sector, with all its electronic components such as the semiconductors. In fact, all the information and communication technologies are also very metal consuming, and their impact is far from being immaterial for the planet. If you consider that we are moving through a 9 billion human society by 2050, it's hard to conceive a decreasing demand in the short or medium term for all the metal of the energy transition. So, are this a signal that we are shifting from an economy essentially dependent on oil and gas to a new era where the mineral resources used for the energy transition will take this place? We can also ask if this new dependency can be a limiting factor for the deployment of low-carbon technologies. There are no simple answers to this question. And above all, there is not only one, because there are, as we have just seen, a multitude of different elements. That's why, in order to try to answer this question, societies and politics carry out criticality analysis. Let me introduce you to this notion of criticality. A good illustration is to consider the criticality of a raw material as a result of two factors. First, the strategic importance, related to the current and future economic weight of the resource. Secondly, the risk of supply disruption. This type of matrix is used, for example, by the European Commission to assess the criticality of raw materials for Europe. The closer the positioning of the raw material is to the no-risk corner of the matrix, the more critical the element is considered. For example, cobalt found in some batteries is considered to be of great economic importance for Europe, with a relatively high supply risk, making it a critical material. On the contrary, gold appears to be an uncritical element for the European Union. Well, we have a good picture view here, but how exactly do we position this element? In the end, criticality analysis is similar to risk analysis. The question are therefore, what are the existing risks, and how are they measured? Well, they are numerous and difficult to quantify on a global scale, and that is why the answer is not as simple. But give me a few minutes to present you some examples of the main risks that can be considered when evaluating the criticality of a raw material. First of all, and as you can see on the map, the countries holding the resources necessary for the energy transition are very different for the oil-producing countries. Some resources are geographically very concentrated. This is the case for cobalt in the Democratic Republic of Congo, for example, or for many rare earths in China. There is therefore a strong chance that new major players will emerge and change the existing global governance of energy today. In addition, like oil-producing countries, these countries may have national strategies that can constrain supply and affect the price of raw materials. This was the case, for example, for the rare earth market in 2010, when China threatened an embargo on Japanese markets. This crisis has raised awareness of the geopolitical issue related to supply. In 2014, Indonesia, one of the main suppliers of nickel, decided to ban direct tapping ore in order to capture more add value through nickel refining. This decision force the market to find other sources of supply. In addition to the geopolitical risk, there are also risks related to economic availability. This is particularly the case for many products that are only extracted as a core product. The indium, for example, 95% of indium supply comes from zinc mine operation. Its availability and ultimately its price are therefore dependent on the zinc market. One way often mentioned to overcome a lack of metals is recycling. However, as indicated in this table, many materials are nowadays very poorly recycled. Recycling processes for small metals, which are embedded in complex matrices, are often difficult and require a lot of energy. So they are not cost effective. Consequently, it is cheaper to extract resources directly from the ground. An increasingly significant risk is also related to the environmental impact of extraction processes and the acceptability for society. For example, lithium mining in Chile is a major water user, while the region is known to be regularly under water stress. There are regular public demonstrations for greater consideration of these factors and more responsible exploitation. So, we have just seen some risks, but they are far from being exhaustive. To obtain a global vision of the criticality of a raw material, it is therefore necessary to take these different risks into account and quantify them in order to determine the criticality of the raw material studied. Using our prospective modeling tools, we are developing climate scenarios at IFPEN for the year 2050 to study the impact of future demand for this material on a global scale. In this way, we put into perspective the various apparent risks on the market and try to shed light on the strategic choices that can be made by public and industrial actors in order to mitigate the impact related to the demand for a given resource. In the link below the video, you can find the latest note on the impact of the transport sector electrification on the lithium market. You will also find the link to the Generate research project on which we are currently working, which aims to analyze the geopolitical consequences of the deployment of renewable energies. So, how we have seen, criticality of a mineral resource is not only geological, but also, and above all, as with oil, it's an economic and geopolitical issue. Finally, to succeed in the energy transition, it's essential to have a systemic vision concerning the various aspects involved, including the demand for mineral resources, but it's not the only one. Only in this way can the most relevant choices be made for the benefit of society. Thank you for your attention.